Hi, I'm Zian, and my project is on evolving neural networks to process problems more efficiently. So basically, in our brains, we have all these different types of neurons that help our brains process problems more efficiently. However, when we look at artificial neural networks today, they really struggle, or they really consist of the same type of neuron, copy and pasted over and over. And because of this, they really struggle to process these same problems efficiently. And so basically, my project is introducing these different types of neurons to these artificial neural networks. And so first off, just to understand how we're going to evaluate these neural networks, basically we're using something called the Zohr problem, and it's basically a problem with two inputs, one output. You don't really need to know how it works. However, we're basically stacking up this problem n number of times. And so typically I'll refer to this as like 1 or 5 Zohr, which really just means the same problem stacked up one time for 1 Zohr, two times for 2 Zohr, and so on and so forth. So when we look at HyperNeat, which is just an algorithm for evolving these neural networks, when it's pitted against 1 Zohr, which is just one of those problems, it solves it really well. And that's because it only has two inputs to worry about. It's really got no problems. However, when we scale this up to 2 Zohr, where it's even just two of the same problem, HyperNeat really struggles. And then 3 Zohr and 4 Zohr. And you can see this on the graph with the fitness. Attaining a fitness of 1 means that you've solved it. And you can see how 2 Zohr, 3 Zohr, and 4 Zohr really aren't getting solved, much less 5 Zohr. So in order to sort of circumvent this, we can actually pick these different types of neurons beforehand. And so basically the way we do that is we select different points on the neural network, different nodes, and then we sort of say, hey, you're going to be this specific type of neuron. And so when we're looking at that, we can sort of standardize the way that the network processes problems. Because like every Zohr problem, for example, like every little Zohr problem module, will have one of this type of neuron, one of this type of neuron, and one of this type of neuron. And that basically allows the neural network to process it way more efficiently. And you can see this in this graph where you can see the dotted lines are all the FCS HyperNeat algorithms versus basic HyperNeat. And FCS is just a fixed chemical substrate. It's how we're cherry picking or how we're picking the different types of neurons. However, the problem with this is that we have to then specify each different type of neuron. And so on the left, you can see sort of HyperNeat has this very clear gradient as far as types of neurons, whereas sort of I had to specify for FCS HyperNeat this really weird shape on the right in order to get it to have those results, in order to get it to process that problem more efficiently. And so the Zohr problem is actually quite simple as far as sort of stacking up. It's the same problem again and again. And so it makes finding that shape a lot easier than it would be for something like a lunar lander or an actual application. And so in order to automatically find these sort of structures or these 3D plots, we can actually allow the neural network to evolve its own different patterns or these different plots. And so by doing this, usually when you have a neural network, you sort of pass in the inputs and then it'll output. You'll have the neural network in the middle and then it'll output sort of the values that you need. With sort of evolving these patterns, we actually pass in some inputs. They go into the neural network, right? They come out and then they go back into the neural network. And then they go out into finally the sort of output that we read. And so by doing this, we effectively allow the neural network to determine its own different structures. And so we can see a visualization of this. This is all in one run. And these are only the best performers of that run. It explores all these different possibilities for structures automatically. And this allows it to very consistently outperform HyperNeat. You can see ECS HyperNeat is just the name for this. And it's in the blue, and even in like 2,500 generations, which is like no time, you can see that it very clearly outperforms HyperNeat. And as we go and sort of zoom out and we go to like 50,000 generations, you'll notice that even though ECS hyperneat doesn't completely solve every single run, you'll notice there's a very big gap between like hyperneat solving at like 75% on average versus ECS hyperneat solving on like 85%. And so there's this very clear difference. And what's also interesting is that although all the hyperneat algorithm sort of neural networks sort of converge to that 75% fitness or something very close to that value, the ECS hyperneat sort of algorithms, they're different runs. Some of them are actually outliers, and they end up solving the Zor problem because they stumble across that same pattern that I discovered. And so because of this, it very consistently outperforms uh, hyperneat as a whole.